Hey everybody, Dr. Rudzik here. This is our second video on 14.5, and it's a little further discussion on the gradient. So here's where we are so far in 14.5. In 14.5, we've been studying the directional derivative in the direction of unit vector u for a function f, and what we have discovered so far is that directional derivative represents the slope that a hiker on the surface, z equals f of xy, would encounter if that hiker took off in the direction of the unit vector u. So in some directions, you'd be going steeply uphill, others steeply downhill, others maybe flat. So it all depends on that direction vector u. Now we have a limit definition for this directional derivative, but in the end, because of chain rule, what it turns out to be is this thing called the gradient, denoted with that symbol, so that's read gradient f, simply dotted with the direction vector u. So this object here, say for a function of two variables, is just the vector with x partial in its first coordinate and y partial in its second coordinate, and that's called the gradient. Okay, this relationship between the slope in the direction u and this vector called the gradient has some geometrical consequences that could be really useful to us. And that's what we're going to discuss today in this short video. Okay, so I want to draw a picture of the xy plane laying flat. So this is our classic picture like this. So x coming out of the screen, y going to the right. And I want you to imagine that we're looking at a level curve for some function. And that level curve in red, maybe it looks something like this. So that's a curve laying flat in the xy plane and represents all the inputs x comma y that make some function come out to a constant value. So maybe this is the level curve. Level curve f of xy comes out to c. So these are all the inputs x comma y that make f come out to c. So if you were to imagine plugging those inputs into your function f, well, they would all produce the same z value. So floating above that level curve and living on the actual surface, z equals f of xy, you would have outputs all at the same height. So these are directly above the corresponding inputs down there, and they're all at constant height. So this curve, this is the outputs, all constant. Z comes out to C. And it's what you get by plugging in that level curve to your function. Okay, so you have to imagine superimposed on this is the surface itself. So there's a mountain range that you're looking at, but you're only looking at the path around the mountain at constant altitude, z equals c. Okay, now let's think about what this has to do with the gradient. Okay, so if you were interested, say, in this point x comma y, right there, flat in the XY plane, then this would be the point you get out when you plug it in on the actual surface. And here's the key point. If you had a hiker on this trail, walking on that surface, look with your eyes at that picture and ask yourself, what slope would the hiker detect passing through that point? The answer is that they would detect no slope at all, because all points on that trail, the trail that hiker is walking on, it's at constant height, z equals c. So it would be like circumnavigating Bishop Peak, all at altitude 1,000 feet. So the trail might wind left and might wind right as far as the hiker is concerned, but the altitude on the trail doesn't change at all. So that means the slope that the hiker is encountering through that point is 0. So 0 is the slope in the direction of this blue vector Remember, the hiker is walking along the curve. The slope in that direction, so let's call that vector u, down there flat in the xy plane. The slope in the direction of that vector u of our function, whose graph we don't see, and only whose single level curve is depicted in that diagram. Specifically at the point x comma y, it's 0 because that trail is flat. Okay. On the other hand, if our function is differentiable, so say if our partial derivatives at that point exist and are continuous near that point, if the function is differentiable, then we know that that directional derivative is nothing other than the gradient at that point dotted with u. Okay, look at that string of equalities. 0 is how this dot product comes out. Now you have to rely on your Calc 3 knowledge. Two vectors have dot product equal to 0 precisely if the vectors are perpendicular. Therefore, since that dot product comes out 0, you know that the gradient is perpendicular to u. So the gradient, if you were to draw it in green, is perpendicular to the blue vector, flat in the xy plane, like maybe like this, where that angle right there is 90. It could also be pointing outward. I'm imagining this being on a surface that looks like this. And so I'm thinking of the gradient as pointing in the direction straight uphill, and we'll discuss why that's not too big of an assumption in a moment. But whatever direction the gradient points, it's definitely perpendicular to the vector u. So this down here, this green one, is the gradient vector. And if the hiker in this drawing were to turn around, take a hard left, say, and point themselves directly in the direction of the gradient, then they'd be walking directly uphill in that drawing. Or if they were to take a hard right in that picture and point themselves in the exact opposite direction of the gradient, then they'd be walking straight downhill. In other words, the directional derivative in the direction of the gradient is telling you information about the slope of that path, which is exactly perpendicular to the constant altitude path that the hiker is actually walking on. Okay, so the takeaway at this moment is, if you're walking on a path of constant altitude on this hike, corresponding to inputs off of some level curve, then the dot product, gradient with vector u, must be 0, and therefore those two vectors must be perpendicular to each other. Now there's even more that comes out of this, and we'll start on a fresh page here. When you have directional derivative equal to gradient dot direction u. So for example, if the function's differentiable, if you know that you have continuous partials in a neighborhood of that point, say, then this dot product equation is telling you all sorts of things, because check this out. That would imply that the directional derivative in the direction of the vector u is, let's see, what was dot product from Calc 3? It was magnitude of the one vector, magnitude of the other vector, cosine of the angle between them. But remember, u is a unit vector in this entire discussion. So its magnitude is 1, which means the directional derivative is simply the magnitude of the gradient times cos theta, where theta is the angle between the gradient and the direction vector u. What's the biggest cosine can ever come out? 1. What's the smallest cosine can ever come out? -1, which means, grand conclusion, the slope detected on the surface is never any more than the magnitude of the gradient and is never any less than negative the magnitude of the gradient. So the slope you feel on any hike is bounded by the gradient at that point. And the maximum slope you could ever encounter, the steepest uphill you could ever walk, is the magnitude of the gradient. And that would only happen if cos theta was 1, meaning theta was 0, meaning you were walking in the direction of the gradient. And the only way you could be going downhill as steeply as possible at slope negative magnitude of the gradient is if cos theta came out to -1, making theta equal to pi, meaning you were walking in the exact opposite direction. 180 degrees from steepest uphill is steepest downhill. So in fact, the gradient is rich with geometric information. All you ever have to do is compute that gradient, and you know the maximal steepness at that point and the minimal steepness at that point. And if cos theta is 0, meaning theta is 90, and you're walking perpendicular to the gradient, then you're not going up or down. You're at constant altitude, 0 slope at that moment. So that's it for the gradient. It's full of information. You guys should think about how this discussion for functions of 2 variables might extend to a discussion of functions of 3 variables. But basically, you're leaving this video thinking, oh, whoa, gradient, super useful. Tells me the direction to walk in for maximal slope, and it even tells me what that maximal slope is. All right, that's it for 14.5. I'll see you next time for an introduction to 14.6. Bye.